Hey, what's up, guys? This is Dr. Vivek Palipram bringing you a bonus lecturette in ECPE 127 Random Signals. In this lecturette, I'm going to solve the problems that we had solved in our previous class on Friday on 24th of April. In that class, I had given you some data and I had asked you to perform some statistical inference on that data. Specifically, this data pertains to my two different workout regimens, namely the CrossFit program and the starting strength program. And the goal was to see whether or not one program is better than the other with respect to sheer volume. And I have uploaded a CSV file called squats.csv on Canvas files. So it will be worthwhile for you guys to download that file and follow along and perform some R exercises on making certain statistical inferences on these two data. So let's get started. The very first question asks you to create a simple folder and then change to that directory. And then I asked you to open R in that directory. The reason why I asked you to do this is because when you open R software, by default, its path is going to be the path where it is installed, but your data may be in some other folder entirely. So let me demonstrate this purpose or this particular problem for you. Creating a folder. I'm using my Linux operating system. You may be working with Windows operating system or even Mac OS X, which may be a little bit more user friendly. So what I'll do is I'll actually go to my existing folder 127 and then I'll try to open R. But the real goal of this problem, number one, is to use or get used to commands like getwd and setwd to find and set the working directory. So you know what, let me open the R software in my home directory and not in my target folder. So I'll open the R software right here, and R is a nice interpreter just like Python or MATLAB, and it gives you a nice command line interface where you can keep entering your commands and find out what's happening. So the first things first, let me use the getwd command to find out what my current working directory is. So I use the command getwd to find my current working directory, and I find that my current working directory is /home/vpalipu. Now my actual files, my file for analysis is present in ECPE 127. So I'm going to set the directory or set the working directory to that folder. So I'll give the complete path here, /home/vpalipu/ECPE 127. And if I were to query getwd one more time, it tells me what my current working directory is. This particular process will be quite useful if your files are present in totally different folder system. If you are unable to set your working directory appropriately, what I would recommend you to do is find out what your current working directory is for R and then move your CSV files explicitly to that particular folder instead of wrestling through getwd and setwd. But these are two nice R commands that you can always rely on. The next item that the handout asks you to do is to read the CSV file using read.csv function. So I'm going to read that file and I'm going to read it into an object called A. So A is equal to read.csv and the file name is squats.csv. Okay, it says that it cannot open the file called squats.csv. Most likely in my system, it is small s, squats.csv, lowercase s. So now there's no error. So that means the CSV file has been read successfully into our environment here. Now let's find out whether or not it has been read properly. So what I will do is I'll just type A and hit enter, and I'll find that it displays all of the contents of that particular CSV file. I have two columns, xfit and starting strength, and in each of these columns you have numbers pertaining to volume of each of these programs. Just like how in C programming language you have a structure and you access the members of a structure using the dot operator, here in this case A is a structure object and you access the members xfit and ss using the dollar operator in this case. So I can create two new variables called xfit and set it to $xfit and starting strength, which is equal to $starting strength. So these are my two variables that I will be relying on to perform all of the operations. So essentially in this step, what I have done is I have imported the individual columns of my CSV file into two new variables defined by myself, and they are easy to use, xfit and ss. It's always a good idea to type them out and check if they have been read in successfully. So I find that xfit is indeed the very first column and ss is the second column. So that means my data has been read properly. Sometimes R does not give you an error if you are reading an incorrect column. It's not going to give you an error, and if you were to proceed with your analysis, then that's going to be incorrect. So make sure that you check your data, make sure that all the variables are pointing to the right items that they should be pointing to. So that's problem number 2, how to use the read.csv file. Next, let's find out some descriptive statistics for these individual columns. So I have my two programs, xfit and starting strength, and these are the volumes in these two programs. Descriptive statistics are your mean and standard deviation. So whenever we speak about descriptive statistics in the realm of statistics, they always invariably mean the mean or the average value and the sample standard deviation, the sample mean and the sample standard deviation. So let me declare a variable called xfit mean. So that is equal to mean of xfit. So I'll use the mean function, and xfit standard deviation is equal to SD, the standard deviation function of xfit. And I'll type these values out. So xfit mean, that's equal to 602.5. So that's the volume for the xfit program, and the standard deviation, xfit SD, is 296.16. So that's the standard deviation. Similarly, I will obtain the descriptive statistics for the starting strength program. So let me press the up arrow key and name the variables just like how I have named for CrossFit. So mean of SS, and this will be SS mean, and then I have the standard deviation of starting strength program. So mean is 573.33, and the standard deviation for this program starting strength is 101.94. Now, if anyone were to ask you, hey, which program has more volume than the other, you may look into the descriptive statistics and find out that, hey, you know what, xfit's average volume is 602.5, and starting strengths average volume is 573, and you may incorrectly conclude, or rather prematurely conclude, that xfit indeed has a larger volume. Descriptive statistics are great. They give you a little bit of picture as to how the data is distributed, but they are usually not alone to, or they are not used alone to perform inferences, or to rather draw inferences. Instead, they are inputs to some other statistical techniques which are then used to make inference about the data. So in this case, although starting strength's mean is 573, which is smaller than CrossFit's mean, but you will notice that CrossFit's variance is, or standard deviation in this case, is much larger than starting strength's standard deviation. So CrossFit program has a larger spread of the volume compared to starting strength. So we may have to rely on some other techniques to draw inferences. Problem number 4 asks you, for a CrossFit program, find the 95% confidence interval for the true mean and provide the proper inferential statement. And then the problem also asks you, is 500 a likely value for the average volume of the CrossFit program? Now in this problem, I'm asking you to perform a statistical inference technique, namely the estimation of a population parameter. So the true mean is actually a population parameter, and we want to define, or rather derive, a 95% confidence interval. This confidence interval will be a range of values which we believe has 95% chance of containing the population mean. Or rather, this confidence interval is going to contain the mean with 95% chance. So let's derive the 95% confidence interval. The 95% confidence interval is derived as confidence interval x bar plus or minus t percentile for 1 minus alpha over 2, where alpha is the error that this confidence interval is not going to contain the true population mean. So you certainly want that error to be very small. Statisticians always tend to use 5%, and that's why you get your 95% confidence interval. 1 minus 0.05 is equal to 0.95 or 95%. Comma, degrees of freedom, which is equal to sample size minus 1 times the sample standard deviation divided by square root of n. So that's how you evaluate the confidence interval. In this case, x bar is equal to x fit mean. X bar is equal to x fit mean. S is equal to x fit's standard deviation. And alpha value in this case is equal to 0.05. So first things first, I need to evaluate the t-perc or the t percentile in order to get this confidence interval. So t percentile is obtained using a function called qt. So you can type help qt to find out more information about how to use this function. So when I type help qt, the first value is the confidence interval, which is 1 minus alpha over 2, that probability, and then you have the degrees of freedom, which is equal to n minus 1, where n is the size of your sample. In this case, the size of the sample is equal to 12. Each of these two columns have 12 items. So n is equal to 12. So I'll derive CrossFit's lower limit as x bar minus, first I need to get the t-perc. So t-perc is equal to qt 1 minus alpha over 2, comma, n minus 1. So the value of t-perc is 2.20. CrossFit's lower limit is x bar minus t-perc times s divided by square root of n. And the upper limit will be x bar plus. So high, see, XCI high is that. So I have XCI lower value as 414 and XCI high as 790. And this is how I'm going to make a proper inferential statement. The 95% confidence interval for the true average volume for the CrossFit program is 404.32 to 790.67, which means that there is 95% chance that this interval will contain the true population mean, or rather will contain the true average CrossFit volume. So that's my proper inferential statement. Now in this statement, if you notice here, I have used the pound symbol. Pound is for comments. So I can write my comments in my R terminal like that. But you will be writing all of your statistical inference statements in a nice Word document or in and upload it as PDF for your final exam. You are not going to use R to write your comments. Your comments need to be put in a proper PDF. So that's how you'll make the inference out of the problem number 4, where we are obtaining the 95% confidence interval for the true CrossFit volume average or average volume. Let's solve problem number 5 now. So in problem number 5, I want you to do the same thing, but for the starting strength program. So I would like for you to get the 95% confidence interval. Now, since I have used some of these functions, what I'll do is just change the variables. So x bar is going to be SS mean. Sample standard deviation is going to be some starting strength sample deviation, and it's the same. T-perc is going to be the same, but I'll reevaluate it just in case. 1 minus alpha divided by 2 comma n minus 1. So that's that. and I have starting strings lower is x bar minus t perk times s over square root of n, and upper will be x bar plus. So CI lower, the lower value is 508, and the upper value is 638.015. So this is how I perform the statistical inference in this case. So the 95% confidence interval for the starting strings true average volume is 508 till 638, which implies that this interval has 95% chance that it is going to contain the true average volume for the starting strength program. That's how I'll perform my conclusion or a statistical inference, my true proper inferential statements. For both problems 4 and 5, I also asked you, is 500 a likely value for the average volume for these programs? Now, if you were to inspect the 95% confidence interval for the CrossFit program, which is 414 to 790 approximately, and since 500 is contained in this interval, 500 is a good estimate of the CrossFit's true average volume. So that's true for CrossFit. Okay, I forgot to put my pound sign, and that's why R did not recognize it. Now, but for starting strength program, the 95% confidence interval is 508 to 638, and since 500 is not in this interval, it is not a likely estimate of the true average volume for starting strength program. So this is how we make statistical inference and write our inferential statements when we perform the parameter estimation. In this case, the true average for these programs. So we are finding the range of values where our true average can, which may possibly contain the true average for these programs. Let's move on to the next problem, and that is problem number 6. So my friend claims that CrossFit has more volume than starting strength program, and I would like to perform a hypothesis testing on the statement and provide the inferential statement. When I was going through this problem in the class, I had initially incorrectly constructed my null hypothesis. My null hypothesis is always going to be some sort of an equality statement. So in this case, let's say that I want to check if CrossFit program has more volume. So my null statement H naught will be CrossFit volume is equal to starting strength volume. Your null hypothesis will always be an equality relationship. So CrossFit volume or CrossFit average volume is equal to starting strength average volume. Essentially, xfit mean is equal to starting strength mean. That's my null hypothesis. My alternative hypothesis will be anything but the null hypothesis. In this case, first, in problem number 6, I want to test whether CrossFit has more volume than SS. So my alternative hypothesis will be xfit mean is greater than starting strength mean. And because I have this greater than symbol here, I'm going to perform an upper tailed test in R. That's what I'm going to do, an upper tailed test in R. Now the upper tailed test in R is simplified using the function t.test. So you use the t.test function as follows. T.test, the first argument will be crossfit because I'm comparing crossfit with starting strength. The next parameter is SS. Then the next one will be alternative. And my alternative in this case is upper.tail. It's upper tail, or rather just upper, comma, let's see. Let me just quickly pull out the proper functions that I need to use. My apologies, just give me a minute because I tend to not remember. Or you know what? Let me use the help from R. T.test, help t.test, how to use it. There you go. So first argument is X, which is CrossFit, then Y. In this case, it's by default null, but in our case, it's going to be starting strength. Alternative can be two-sided, less or greater. In our case, it's going to be greater. Don't worry about mu because our average is not equal to 0. Paired will be equal to true because both CrossFit and starting strength programs numbers have been derived from one subject, which is myself. I was the one who was undergoing these treatments. So paired will be equal to true, variance.equal will be equal to false, and confidence level will be equal to 95%. So let me just copy this and paste it right here. Oops. Okay, it seems like it doesn't like it. So let me just follow what I can do from here. T.test, first will be CrossFit, then starting strength. Alternative will be equal to greater because I'm going to perform the upper tails test. Paired will be equal to true. Variance is not equal for these two samples, so variance is equal to false, and confidence level is equal to 0.95. Okay, so that's what my t.test gives me. It gives me the t statistic, and it gives me something called as a p-value, and in this case the p-value is 0.3798, or p-value stands for probability. So 0.3798 is essentially 38%. Now there's an important interpretation of this p-value. P-value is the error, or rather it's the probability that you are, or rather probability that I am wrong to reject H naught. So that's the probability. P-value is that probability. Now in this case the probability value is 38%. So there's 38% chance that I am wrong to reject H naught. And you may be wondering whether we should really reject the null hypothesis or not. 38% chance, it's not like it's more than 50%. But you know what, guys? We are performing a proper statistical test. We want our error to be absolutely small. The alpha value that we were talking about, 5%, that was the threshold. That was the maximum error that we could have tolerated. Now, because since p-val is greater than alpha, which is equal to 5%, I cannot safely reject H naught. So I cannot safely reject H naught. So in this case, I'm going to go with H naught. I wouldn't say that I'm going to accept my null hypothesis. I'll just say that I'm not going to reject my null hypothesis. So I'm not going to reject the possibility that XFit mean, the true XFit CrossFit's mean, is in fact approximately equal to starting strength sample mean. So that's my conclusion based on an upper tails test. Now let me show you how to perform the two-sided tests and why two-sided tests are performed. Two-sided tests are performed for the following reason. Your null hypothesis will be the same. XFit mean is equal to starting strength mean. Your alternative hypothesis, however, will be XFit mean is not equal, which is like equal to with a bar or with a slash over it, is not equal to starting strength mean. That's my alternative hypothesis. Because my alternative hypothesis is taking the form not equal, which essentially means that CrossFit's true mean may be even either greater than starting strength's true mean, or it will be less than starting strength's true mean. It can be either of these two. It's two-sided, and that's why I'm going to perform a two-sided t-test in order to test the alternative hypothesis that CrossFit's true mean is not equal to starting strength's true mean. And for that, I'll still use a t.test function, and just I'm going to change greater to two-sided and see what it gives me. It again gave me a t-statistic value, which is 0.313, and it also gave me a p-value, which is 75%. So here, 75% is the probability, or rather 75.97. This highlighted one right here, is the probability that I am wrong to reject H0. And since my threshold is 5%, p-val here is higher than that threshold. It's higher than that threshold, and therefore I cannot reject H0. So there's some evidence. So there is some evidence to show that CrossFit's true mean is perhaps equal to starting strength's true average volume. Let me be more specific here. That there's some evidence to show that CrossFit's true average volume is perhaps equal to starting strength's true average volume. So this is the kind of statement that you're going to give to your customers who are coming to you with their data for analysis. If you give them an inferential statement which is highly mathematical, they are not going to pay you money. You need to talk in a language that they are able to understand. So this is what you're going to say. My statistical analysis, this is for statisticians, or those people that are interested in numbers. This statement right here, 75% is the probability that we are incorrectly rejecting H0. Since our threshold is 5%, p-value is higher here, therefore we cannot reject H0. Now the real selling statement will be this one. This is for your customers. There's some statistical evidence to show that CrossFit's true average volume is perhaps equal to the starting strength's true average volume. So this is what I'm going to look into as a customer, and then I'm going to decide, hey, you know what, whether I should switch from CrossFit to starting strength. Now, it has now given me some reasonable faith that starting strength does have a similar volume as CrossFit, so I will definitely grow bigger if I were to perform starting strength. Just like that, I love starting strength because I'm able to pack on more weight as I progress through my workouts. So with this statistical analysis, I'm confident, or rather I am sure, that I'm going to pursue starting strength program for some time. In your real life, you can also perform such an analysis. If you're confused about choosing one program or the other, just collect some reasonable data for these two programs. It can be anything in life. It can be a simple pros and cons list with some numbers, and you can use the statistical testing to guide your decision making. So that's all I have for this lecture. It's a bonus lecture where I solve all the problems that we have discussed in Friday's class. Please go through this. I'll post this on YouTube, and if possible, if time permits, I'll also put the timestamps which tells you where I solve a particular problem, so you can go through it. Adios, guys.